as you're watching here. Hopefully you'll still see me up in the corner. That's me in the corner. I won't start singing the REM song, Losing My Religion, for those of you who aren't old enough to remember that song. But this is chapter 8, and I'm going to highlight a couple of different things as we go through this, because I can play the slideshow, and we'll talk about geology. Earth is a planet. You can sort of see it in the background here. We have lots of different things that distinguish us as a planet from other planets, but there are lots of things on our planet that are similar to other planets as well. So knowing what's happening on our planet will help understand other planets along the way. We have active geology. We have volcanoes, we have glaciers, we have waterfalls, we have oceans, we have wind, we have erosion of all different sorts. When we look at things like this picture that we have here, this is one of the Aleutian Islands. This is just off of Alaska. This is similar to the Hawaiian Islands. These are actually mountaintops, and these are mountaintops where the base of the mountain is actually underwater. So when we look at these islands here, these are actually the tops of mountains that were made over time. This is similar to the picture I've got behind me. This is Apollo 17, which was one of the last major missions off of our planet that had people. We have, of course, different missions to the space station and the shuttle and other kinds of things like that. But in terms of going out beyond our planet all the way to the moon, Apollo 17 is sort of our last big shot. This is sometimes called the blue marble shot because you see the dominant color is blue. That's water. But also this white stuff down here, which is solid, that's ice, that's Antarctica, that's also water, H2O. This white stuff around here, clouds, gaseous stuff, that's also water, H2O. So we have H2O in 3 different ways. We have it in solid, liquid, and gas form. So we call that being at the triple point. This is one of those rare pictures of the Earth where we get the whole thing, because in fact the sun was behind the person taking the picture. If you were taking the picture from over here, you'd only actually see about half the Earth because half of it would be in shadow. So this is a unique picture in many ways. Our Earth has an interior that can be sort of simply modeled. We have an inner core that is mostly solid. We have an outer core, or we can just call that the core, which is mostly molten. So we have sort of solid and liquidy kind of thing. It's rather slushy, but it's not cold slush, it's hot slush. And then we have the mantle, which is rocky stuff, and the crust, which is where we live on top of that. As we are looking at the interior of our planet, the densest stuff, iron, nickel, other kinds of stuff, have sunk to the bottom, and the lighter stuff is at the top. So as we go from the inside to the out, we get less and less dense. We get heavier and heavier material as we go towards the center from any direction along the way. Notice this dotted line here, lithosphere. We'll come back to that in a moment. The process by which the denser stuff falls to the center is called differentiation, because as this stuff is not completely rock crystal solid, but things are slushy and moving, there's magma, there's molten stuff in here, the hotter stuff eventually settles closer to the center of gravity, which is going to be the center of the Earth for us here. The lithosphere, as I mentioned before, this is the part that is exposed to space, more or less. We have an atmosphere that helps insulate us, but it's mostly exposed to space. Heat is leaving the planet here. We are, in fact, cooling off, and we cool off from the outside in. So as we cool off, this lithosphere, this dotted line, will sink further and further and further down over time. Smaller planets cool off faster. Larger planets cool off more slowly. But underneath this, we have stuff that is still molten. So the stuff on this top here, which tends to be rigid, floats. And that's why we have earthquakes and other kinds of situations that involve the shifting of our tectonic plates. We'll talk about that here in a moment. As we can see, our crust, we have part of it covered with ocean. In fact, it's mostly 70% ocean. And then we have part of it that is land, that is high enough to be above the oceans. These land masses shift back and forth. All of our the surface of the planet is moving in tectonic forces. As we spin around, our molten core, because it's not solid, is sort of slushing around and it's having some friction. It's creating, because it is iron and nickel and other metallic forces that are sloshing around in there, it's generating a magnetic field. So we have shields up. And from the sun side over here, as you sort of see on this side, as the solar wind is going in this direction, it's hitting our shield as we're spinning around like this. And as the particles go past here, it expands out in the other side of our space around our planet, the magnetic fields. We call part of them Van Allen belts, and we have other magnetic forces around us along the way. We can actually measure those with satellites up in orbit. Let's see, let me undo what we've done here so that I can go on to the next slide. So I'm still learning this, so forgive me along the way. If a planet has three things, as you see here, we will have a magnetic field. Here on Earth, we have all three things. We have a molten core. We have a moderately rapid rotation. We're sort of going around once every 23 hours, 56 minutes. Roughly 24 hours. And we also have convection bubbles. We have the hot stuff rising, it releases its energy, and the cooler stuff sinks back down to the bottom. So we have all three of those. Not all planets have all three. For example, Venus will not have a moderately rapid rotation. It's very, very slow, even though it might have the other two. One of the things that's happening on Mars is it rotates about the same size, time as we do, but it doesn't have a molten core anymore. It's cooled off. So when we look at our magnetic field, we can see the particles coming off of the sun hitting us, extending our magnetic field out towards the back. But some of those particles get trapped in our magnetic field around the polar regions, and that's what gives us our northern lights, our aurora borealis. And let me show you here just a moment. I have one of these virtual background things which has the northern lights, and you can actually see northern lights going back there. You'll see these in Iceland, you'll see these in Alaska and Canada, you'll see these in a lot of northern places. You'll also see these down around the South Pole in Antarctica along the way. So just wanted to sort of show you some of that there. So let's go back to our share screen and go back to our slideshow. There we go. And there we go. Trying to get it to work. The magma that is under our surface, once it reaches the surface, is called lava. Really, magma and lava are the same thing, only lava is exposed to the atmosphere and thus changes a little bit chemically and mineral-wise. But this is all volcanism, so live long and prosper. Volcanic activity is found on every continent on Earth in one form or another. Sometimes it's at the surface, sometimes it is rumbling below the surface, but below the surface it tends to be called magma, above the surface it tends to be called lava, and it begins to cool off. There are three main types of volcanoes. We have lava plains. There are big ones on the moon, and when we talk about the moon in a later lecture, we'll talk about those more directly. We have shield volcanoes, and that's where the volcanic activity, let's see, can I get my annotations going again? Yes, here we go. So the magma sort of comes up and builds it up and builds it up and builds it up like that. And the largest example of that is Olympus Mons on Mars. That volcano is the size of the state of Missouri, but we have some on Earth as well. The Hawaiian Islands tend to be those. And then we have our stratovolcanoes over here. Those are the kind that just sort of go up and the lava shoots straight up. Those are the kind that if you're going to look at volcanoes on cartoons like the Flintstones, that's what will be happening there. One of the most famous ones of those is Mount Vesuvius, which is what buried the city of Pompeii. Mount Fuji in the background of Tokyo pictures is one such. And we have others here on Earth like Mount Hood and Mount St. Helens in Washington State here in the United States. We have a hot spot in the middle of the Pacific, and that's where the Hawaiian Islands grow. These are the sort of bubbling up results of shield volcanoes. But notice we've got this very, very long chain of mountains. This is actually a mountain range, most of which is underwater. It's only as the plate is sort of moved around, the plate moves around, and there's this hot spot that bubbles up and bubbles up and bubbles up and bubbles up. And as the plate moves, the mountain forms, but then it forms another, and then it forms another, and then it forms another. If it stops for a while, it builds up enough that the top of the mountain reaches the surface. This little flat island here is actually a mountaintop of several miles down. Then the big island of Hawaii here is where the hot spot has gotten stuck for a while. The plate had stopped moving. But the newest Hawaiian island, Loihi, is just forming off the south coast down there. So get your condo reservations now, because in about 1 million years, we'll have an island there. One of the first persons to figure all this out, and the first person to really put together a consistent proposal about all of these plates moving around, is Alfred Wegener. Like many scientists, people poo-pooed the idea when he first put it forward, but he ended up being right, of course. As we look at the different plates, we have about a dozen major plates on our planet. Some are much bigger than others. As you can see, the Eurasian plate up here, the North American plate, the Southern American plate, the Africa plate. They're moving in different directions. We also have subplates, like this area here is called the subcontinent. That's India. And I'll show you just how we know that's a subcontinent here in just a moment. Looks like it's attached to the Eurasian plate, and it is, but it's actually a separate kind of thing. Notice the Atlantic Ocean here is separating out. Part is going that direction, part is going that direction. So we've got a big ridge that goes down the middle of the Atlantic, and it starts near the North Pole and goes all the way down almost to Antarctica, and it's separating out. So Europe and the Americas, Africa and the Americas are getting farther away from each other. Notice this here and this here, they look like they used to fit together. In fact, they used to be together. Notice this here in Madagascar and this here in Africa. They look like they used to be together. Guess what? They used to be together. There's a portion here and a portion here that used to be against this as well and against this down here. There are different places that have been in contact with each other and have shifted and moved over time. Sometimes things are pushing together. The Appalachian Mountains are actually formed when the east coast of the United States was bumping up against Africa. So looking back here, this portion, oh, can I get my drawing thing back again? Thank you. We can, sorry, oh, I want it to go back here though. Nope, it's not working for me. Stop here. If you look here, this portion of the United States used to be up against this portion of Africa. That's a long way away. But a long time ago, when they were against each other, they were bumping up against each other and compressing things and pushing things up. And that's where we got the Appalachian Mountains. Sometimes things spread apart, and that creates valleys and canyons along the way. This mid-Atlantic ridge here is one of those. And most of it's underwater, except for a portion that's very near the north. And that is this place here, and that's called Iceland. That's the only part of the mid-Atlantic ridge that is above the ocean. So I go there and I stand in one spot, and part of me's in Europe and part of me's in North America. And I have stood in one spot, and then over the course of years, I have to stand further and further and further and further away, because it does separate out by a couple of inches each year. And I can no longer fit my feet on the place where they used to be about 40 years ago when I started going to Iceland in earnest. You can see here where things are bumping together. Oops, come back. You can see over here in the Pacific area where the Pacific plate is bumping up against the American plate. We've got huge mountain ranges. These Pacific plates are bumping up against South America, big mountain ranges. The India plate is bumping up. This is actually a subplate up against the Asian plate. We've got big mountains. So where those things bump up against each other, we tend to get compressions. Here you can see how South America and Africa used to fit together rather neatly. As things separate out, of course, the portion between them often turns to ocean, and it's very thin, it's newer. The continents tend to be a lot thicker. That's one of the reasons why people will go out and drill in the oceans, because it's a lot less to drill out here than it is to drill in the deeper parts of the rocks. Here we can sort of see our plates moving on the convection cells. See some of this seafloor crust over here in the Pacific is going under the North American plate. It's pushing up the mountains. Notice there's a volcano there. We have earthquakes there. The plate is going under. It's being re-melted. It's being remoltened down there. Up here, we have the Atlantic Ocean separating out, so we have new plate being formed as it cools against the ocean. If it's going under, it's called subduction. Sub as in subway, or under along the way. Here's North America. Here over on this side, the West Coast, we have lots of mountain ranges, Rocky Mountains down into Mexico, up into Canada, here all the way along. The Pacific coast has lots of volcanoes and lots of earthquakes. Here's the old crunch spot where the United States used to be up against Africa. And we have the mountain ranges there, not nearly as big because we're not bumping up against them anymore, so they've eroded down. But notice we have this crack here. That's what gives us here in Indiana earthquakes. You may have experienced those yourself at one point along the way. Here we can see in this bottom graphic here a subduction zone. Notice the plate here going under the other plate. As it hits the melted zone, it begins to shoot up some magma to release some pressure. As things are separating out in this upper graphic, it's called a rift zone. There's a separation or a rift. We will often get volcanoes around there too. Sometimes those will be under the ocean, though we won't actually see them from where we are. And here is a good picture of that India plate I was telling you. This whole area here, let me see if I can get my little drawing tool again. This whole area here, you can see exactly where this plate is bumping under this plate. It's pushing all of this stuff up. So this is where Mount Everest is, the tallest mountain in the world. This is where K2 is, one of the tallest mountains in the world, because this is pushing up under this. So this is rising higher and higher and higher along the way. So the Himalayas are often called the rooftop of the world. And of course, this plate is pushing under. So this used to be separate entirely from the rest of the Asian plate along the way. Here we can see the Red Sea, and it is separating out. So we have the Arabian Peninsula, and Israel and Jordan are over here. Egypt is over here. It's separating out. So as it separates out, the Red Sea gets wider and wider. We have earthquakes in this area. We have volcanoes in this area. That's the Sinai Peninsula. You may have heard of a place called Mount Sinai that had rumbles that was in this area. You may have heard of cities called Sodom and Gomorrah being destroyed by fire and brimstone. That sounds an awful lot like a volcano. That's over here as well. And we have lots of earthquakes and volcanic activity in this area, as well as tsunami action when the Red Sea experiences some of those earthquakes along the way. So we have historic memories in some ancient literature that talk about some of the geological formations that are happening around there. Let's see, will it let me go? Yes. And here's the San Andreas Fault. You may have heard of this. This is one of the key things about California that makes it dangerous to live there, because this is a very active place. This right here, this is the Pacific plate, this is the North American plate. They're bumping up against each other along the way. And when they separate out, look at this. I mean, this is rather dramatic. Will it let me annotate? Thank you. Notice here, notice here. That's a huge separation from where one plate went in that direction and one plate went in that direction here. We can see the Pacific plate is turning towards that. The North American plate is grinding a little bit in that direction, and the Pacific plate is also moving up under the North American plate. So we get lots of volcanoes and lots of earthquakes all along that area. Get rid of all my markings here. And as we can see, over time, we have the plates moving and moving. Here's where we are now. Eventually, things will shift. Notice Antarctica, where the South Pole is, moving up. Notice India's pushed a little bit more. Notice we have a sea here, the Mediterranean, that will disappear. Oops, that will disappear in this area here in 150 million years. Notice 200 million years ago, everything was all together. This was an area that was called Pangea. And if you go to YouTube or some such, maybe someday this will let me annotate. Great, thank you. It's called Pangea. Pan as in everything, Gea as in geological. Do a YouTube search for that, and you'll see a couple of different kinds of videos where you can watch the shifting of the tectonic plates along the way. Oh, I want to get rid of that annotation. We don't need it there. When we have earthquakes, we have different kinds of waves. We have P waves, which are called pressure waves. They just sort of go back and forth like this. And then we have the S waves. They're called sinusoidal waves. And if you've ever seen a bridge, a video of a bridge going like this, then one of the things that is happening there is it's being hit by the sinusoidal waves. We can actually reinforce buildings against pressure waves going like this. But when you're twisting and turning, that becomes harder, and that's where you get a lot of damage. But fortunately, the Earth blocks most of the S waves. The sinusoidal waves don't move very far. But the pressure waves, the P waves, go through most of the Earth. So we can register earthquakes everywhere on our planet. There are thousands of earthquakes every single day here on our planet. Most of them are too light to register. But we have here in Indiana, right next door to us at Indiana University, a place called the Indiana Geological Survey, and they help keep track with a bunch of other places worldwide of where earthquakes are happening. As earthquakes are happening, everything is moving around the planet, and we have to adjust our GPS trackers so that we know exactly where things are because the whole surface is moving along the way. There are other ways in which our surface gets reshaped, and one of those is water. This is the Grand Canyon. This is a mile deep. This river, the Colorado River, has just been snaking its way through the terrain of the southwestern North American continent for quite some time. And as we see, we can look down and see the various geological strata. If you've taken earth science classes before, we talk about the different kinds of geologies that are taking place there. Then we have erosion by ice. This whole area here used to be a glacier. And as the glacier receded, it tore apart some of the mountains here. We've had some glacier activity here in Indiana. Martinsville, for example, if you're a person from Martinsville or were part of a high school that played people from Martinsville, they're called the Artesians. And the Artesians are the fighting well waters. It's like, what's an artesian? Well, the reason why we have artesian water there is in part because of the last ice age. The glaciers that covered this part of North America stopped right around Martinsville. They didn't make it as far south as Bloomington. And when they began to melt, the water seeped into the water table there and changed the water a little bit and changed the geology a little bit. Have you ever noticed if you're driving north towards Indy and especially up towards Chicago, how things get very flat? But as you're driving south towards Evansville or Louisville, everything gets undulating. That's because of the glaciers. As the glaciers melted, it, in fact, flattened everything out. We still have the glaciers to this day. You know where they are? The Great Lakes. The Great Lakes are melted glaciers. That's why they're freshwater and not seawater. They're not salt water. They are melted ice. They are melted glaciers. Here's another great effect from water freezing. Water, when it freezes, expands, and frozen water is crystal and it's hard. And it can actually be harder than the rock and stone around it. So if you get water droplets inside of rocky areas, when it expands, it will break the rocks. And that's exactly what's happened here over time. It's dramatic, isn't it? I love this photo. We have erosion by wind. This is sometimes called cantaloupe terrain. We will see that term again when we're looking at different planets and moons, but we sort of have the undulation of the sand dunes here. If you have wind hitting something for millions and millions and millions of years, it doesn't have to be very powerful to wear things away. Then we have erosional debris. This is stuff that floats down the river and sort of builds up and up and up from the stuff that's floated down. Most of the people in ancient Egypt lived on a debris plain of the stuff that floated down the Nile. About a third to a half of the state of Louisiana is a debris plain that's here. Lots of people live in countries like basically the whole country of Bangladesh is a debris plain from a major river. Lots of areas in China, lots of places in Southeast Asia, lots of places around the world are debris plains because they're very fertile. As you can see, there's lots of plants and animals that grow in these areas. Above us, we have an atmosphere. We have an atmosphere that gets cooler as we go up, and then it warms up a little bit more, gets cooler. And even if it warms up though, there's so few particles there that it will still be frozen. But most of our atmosphere is actually within the first 5 to 6 miles above us. And most of our weather patterns, hurricanes, tornadoes, clouds, rain, all of that happens within that range. That's not very high up. So typical plane will fly over these kinds of storms. Whenever I fly over to Europe or fly over even to other places here in the United States, we usually will fly above the clouds, not too high up. This is a picture, I wish this were actually a little bit earlier. This is a picture that shows you the extent of the last ice age. And again, as I mentioned before, notice here, this is about where Martinsville is, right here. The ice covered all of Canada and about probably a half of the United States. It covered all of Greenland and Iceland over here. It covered much of Alaska. It covered a lot of Europe and Northern Asia. But it also lowered the sea levels so that people could actually walk across from Asia to the United States area of Alaska here. We weren't the United States back then, of course, but that's what it is now. And then from there, they were able to go through what's now Canada, the United States and Mexico, and down into South America. So there are many anthropologists who believe that the Native Americans of all sorts, whether they're North American Native Americans like the Sioux and the Cherokee and other kinds of tribes that are here, as well as the major empires like the Aztec and the Mayan and the Incan in Central and South America, all originated from Asia, walking across over into the North and South America area during this time. And then, of course, when the water rose because the ice melted, they were cut off. And that's why we had no real contact back and forth for thousands of years after that along the way. But we can tell what's happened over time as we look down into the geology. Here, these are stromatolites. These are some of the oldest evidences of living things on our planet, because stromatolites are these kinds of things that are left over from living creatures. Like snails will leave behind shells when they're done living in them. Different animals, different plants will leave things behind. Stromatolites here build up these forms, sort of like coral builds up forms as well. And we have some of these that have dated back to 3 billion years ago. Some of them we found in Western Australia. Some of them we found in South Africa. Guess what? A long time ago, they were not far away. They were up against each other. So it makes sense that they would be together. The tree of life is very complex. You are here. We're in the animal kingdom. We are near the plant kingdom. We deal with fungi, mushrooms and other kinds of things like that. We've got all sorts of different things that are out here, but notice how very complex all of this stuff is. We're just a very small part. And in fact, bacteria and insects and other kinds of smaller things outweigh us dramatically on the planet. So our planet's life actually exists within about 5 miles up from our surface and 5 miles down from our surface. So not a lot of life too much further down that, and not a lot of life too much further up from that. Our atmosphere is about 10 kilometers thick, which basically means it's about 6 miles. That's where we begin to run out. We don't really have enough to be able to breathe then. It's mostly nitrogen and oxygen. So as you're breathing in and breathing out, you are mostly breathing in nitrogen. 2/3 of what you're breathing in at least is nitrogen. What you're using is oxygen. Nitrogen is inert, doesn't hurt you, nothing else happens as you're doing that. But we can increase our pressure through either adding more particles, blowing into a balloon adds more particles, or we can expand our balloon by air pressure by heating the particles. That's how hot air balloons work. Our atmospheric pressure, as it's sort of weighing down on us, is about 15 pounds per square inch, as it says on the thing here, 14.7 pounds per square inch. That's 1 bar. If you've ever heard of barometric pressure, that's what this is, 1 bar, 1 barometric pressure. Notice that as we go up and up and up and up, there are fewer and fewer particles. So essentially what's happening here is there's not a lot of stuff. It's not very heavy at all. But right now, as I sit here, I've got maybe 6 square inches on my shoulders and 9 to 12 square inches on my head. So I'm holding up several hundred pounds of atmosphere. So I'm a weightlifter, and so are you. But we're just used to it. It's always there. The higher up we go, the less and less and less we have. So if we go up to here, notice how much less the atmosphere is going to have. We won't have enough to breathe. By the time that we get to a certain point to the tops of most high mountains, for example, we begin to struggle with breathing because there simply aren't enough particles left in the atmosphere. Most of our atmosphere, again, is within 6 miles, but by the time we get up to about 60 miles or 100 kilometers, there aren't enough particles to turn the sky blue. And that's where we really consider that we've gone into space. But we can actually go up several hundred miles and still see some tiny particles, tiny amounts of particles that are there. Here's a picture. You can sort of see the back of the space shuttle here, and we can see the northern lights hitting the atmosphere, the particles hitting the atmosphere to create the northern lights here from up above. As we live here on our planet, the area that we live in is the troposphere, tropos, as in tropics. This is where it's warmest. Notice our temperature gauge here. As we go up, it goes down. That's why we have snow on the tops of mountains, no matter where they are on the planet. Mount Kilimanjaro is right on the equator, but it still has a snow-capped peak. So heat rises, and the cooler air will sink back down, and we have convection bubbles. And that's part of what helps create our weather patterns here on Earth. Visible light makes it all the way down to the surface. Some infrared makes it all the way down to the surface. Fortunately for us, most of the UV rays are blocked in the stratosphere, and they're mostly blocked at this area here by the ozone layer. And you may have heard of the ozone layer at different times. Ozone is actually O3. So think about ozone. We often say it's O3. Breathable oxygen is O2. Breathable oxygen has 2 particles of oxygen that link together. Ozone has a 3rd one in there. When the UV rays come in, it hits those 3 particles and breaks it apart into 2 that we can breathe, and then 1 that's off by itself, and it doesn't like to be by itself, so it'll combine with another one that's by itself, and they'll also become that as well. This is a big deal because for a while in the 20th century, we were destroying the ozone layer with different kinds of chemicals that we were producing here on Earth. Since we've stopped producing those chemicals, or at least mostly stopped producing and releasing them into the atmosphere. We still produce them. They're called chlorofluorocarbons. But since we now manage them much more directly and much more dramatically, we're seeing a regeneration of the ozone layer that's there. And that's important for us along the way. Let's see. Okay, I can get rid of that annotation too. I'm still learning, so forgive me. Above that, we have the thermosphere. Notice this is where X-rays get blocked, and that's a very good thing for us too, because X-rays tend to be pretty nasty stuff, as we've talked about before. Temperature rises, but there's so few particles in the atmosphere that you would still freeze up there. And then all the way above that, notice there's this little break here. We're going all the way up to 300-400 miles above. We call that the exosphere. Now, our atmosphere has a lot of other layers that are in there, but these are the key layers that we are concerning ourselves with when we're thinking about planets. And our sky is blue because of the atmosphere. Think about being on the planet and having the sun directly overhead. So if the sun is directly overhead, the light is going through this much atmosphere here. But when the sun is actually at sunrise, or over here at sunset, it's going through a lot more of the atmosphere along the way. So if it goes through only a small portion of the atmosphere, mostly the blue, the more energetic light scatters, and that's what we see. But at sunrise or sunset, notice as the Earth has turned, we are looking and all the blue has actually scattered away, and what's left over is the red light. So that's why the sky is blue during the day. Okay, we're going to restart the meeting. Sorry about that. There were some technical difficulties with everything else along the way. So we will do the best we can. And oops, I have lost the screen again here. Okay, doing the best I can. I apologize for that. Let me share my screen again with you so we can get back to our discussion. We're almost at the end here, so please bear with me. We will try to get the slideshow from the current slide that's here. So what we're going to talk about for the remainder of this is how atmospheres work a little bit to keep planets not too hot and not too cold if they are in the position of the Earth, or how things can go awry. You may have heard about the greenhouse effect. The greenhouse effect is actually something that is good. A runaway greenhouse effect is not good. But the way greenhouses work is light comes through something, and as it heats the stuff inside that something, the heat itself continues to be bounced back around inside. Now, in a greenhouse, this will be glass or plastic or something else that will be a barrier. That will also shield the inside from the rest of the atmosphere. On our atmosphere, it actually tends to be the atmosphere itself, primarily water vapor and clouds and other particles, that when light comes through and warms the surface, the re-radiated out heat in infrared gets trapped and bounced around by clouds, by other particles along the way. Water vapor, methane, and carbon dioxide are key towards keeping us warm. And in fact, we want to be warm. We just don't want to be too warm. So that's what we'll talk about here in just a moment along the way. But we do have a greenhouse effect. The moon does not have a greenhouse effect. The more particles we have in the atmosphere, you see here, this is our standard light coming off of the sun. The visual light doesn't tend to be, they're shorter waves. They tend to bounce through fairly readily. The infrared are longer waves. They tend to be bounced around between the particles with much less agility than the shorter visible waves. So it bounces and bounces and bounces. If you put more particles in here, it stays around longer. And that's what the whole greenhouse gas effect is, the debate's all about. Do we have too many particles in here along the way? Here is what's happening on the nearby planets. Mercury has no greenhouse effect because it has virtually no atmosphere. So in the daytime, it just broils, and at night, it drops way, way down. The moon is also no atmosphere. So on the day, notice it's not quite as hot here. Oops, go back. It's not quite as hot. There's Mercury during the day. There's the moon during the day. Notice the nighttime temperature is the same, but during the day, Mercury's a lot closer to the sun, so it heats up a lot more. Now we, as we go along, actually have a relatively cool temperature. That's an average temperature because remember, we're taking into account the polar ice caps and everything else that's there as well. But we have an atmosphere that takes the warmth and keeps it from all escaping all at once, which is why we don't drop down to this at night. Notice on Mars here, we have our temperatures that are much cooler. It has much less of an atmosphere. Notice Venus here, it's just really cooking. Venus has a surface temperature that is hot enough to melt iron and lead. And that's because it has a very, very thick atmosphere. It is an atmosphere that's 95 times thicker than ours. So of course, it is hugely, hugely greenhouse affected. And that's part of what the issue is when we're dealing with greenhouse effect. So if we want to look at a runaway greenhouse effect, we look at Venus. That's part of our comparative planetology. Now here on Earth, we have particles, carbon dioxide particles, that we've been putting in the atmosphere, partly from factory production, partly from automobile exhaust, partly from different kinds of things that are happening there. Notice it goes up and down every year. And that's because as plants grow, it takes carbon dioxide out of the atmosphere. As they die back in the winter, the carbon dioxide stays in the atmosphere. So it goes up and down, up and down, up and down. It's gone up from about 300 to 400 particles per million. That's what ppm means here. So it's not a huge amount, but it's enough to make a measurable difference on our planet. But it's not the only thing that's changing our climate. Our climate has always been changing. That's why I mentioned earlier in the semester, if you know someone who says, oh, there's no such thing as climate change, it's like, okay, turn the channel, stop watching that news show, and watch what's happening. We've had climate change all throughout history. Remember I talked about Martinsville and the Ice Age? Climate change. Climate change happens. It is a natural process. Part of it is the sun is getting a little bit brighter over time, and that gives us a little bit more warmth over time. I have literally listened to a radio commentator who on one day as I was driving up to Indianapolis said, there's no such thing as global warming. And then the very next day, and I was stuck listening to this because I only had an AM radio in that old beat up car, so this was the only thing that was on, I had no choice. The very next day, the same radio commentator said, well, of course the Earth is getting warmer because the sun's getting hotter. And I almost stopped the car and said, did you not listen to yourself yesterday? Yesterday you said it didn't exist, and today you're saying it does. So pay attention when people contradict themselves, because often they don't know what they're really talking about. He was right. The sun is getting hotter. But here's the thing. The sun is getting hotter, so we should be able to measure how hot each of the planets is getting as a result. And we measure Mercury's getting hotter, Venus is getting hotter, Mars is getting hotter, but the Earth, oops, it's getting even hotter. So that's not the only thing that's operating here. We also have a tilt we've talked about before. I'm always sort of leaning over this way. We are tilted at 23.5 degrees, but sometimes we're tilted a little bit more, sometimes we're tilted a little bit less. That actually does make a difference in our temperatures. Also, sometimes we're pointed at Polaris and sometimes we're pointed at Vega. Well, guess what? 10, 12,000 years ago, we were pointed at Vega. What was happening then? There was an ice age. So these things happen as well. These things make a difference. Changes in reflectivity also matter. The ice caps on the top and the bottom reflect more light. The Earth itself, the dirt that's there, reflects less light. So the more ice we have, the more reflectivity we have and the less we heat up, which means as the ice caps melt, we have more warming that's taking place. But here's the thing that happens on our planet over the long term. As we get hotter, then we put more particles into the air of water vapor. We have more cloud cover, which then reflects more light off, and that cools us down, which means we have fewer clouds and less evaporation, which then makes us warm up. So we warm up and cool down and warm up and cool down. We have this happening. This also has CO2 in going up and going down, depending upon how much we have happening in the atmosphere. When we have cooling, we have CO2 building up in the atmosphere. That makes us warmer. When we have heating, we have rain that will reduce the amount of carbon dioxide in the atmosphere, and that will make us cooler. So we do actually go through cycles. That's why ice ages come and go. That's why other climate change processes come and go. And sometimes we've even had a completely covered planet in terms of snow. I'm going to look for a video on YouTube, and you can look for it too, called Snowball Earth. And a couple of times in our history, at least once, perhaps more than once, we've been completely covered. Right now we're sort of like this over here on the end. We have some ice caps, we have a lot of area of liquid water. This isn't frozen solid, by the way, these two in the middle here. It's just like going fishing on an ice pond. You can drill through or saw through and drop your line in, and there's still fish under there. It's not frozen all the way down. There are also volcanoes under here, and the tectonic shifts, the plates are moving around, that'll break things up. So as we wobble around, and as we sort of adjust our tilt up and down, and as our plates move in different directions, and as the sun heats up, all these things are causing climate change. Our climate is always changing, 100% of the time. So no one should ever believe that we are not in a climate change situation along the way. But here's what we need to pay attention to. Are we making it worse? Are we making it worse than it needs to be? We have our carbon dioxide going up over 50 years. That's just science. No one is disputing whether or not we have more carbon dioxide in the atmosphere. There's not one credible source. The debate right now is, how does that affect us? Here's one of the things to watch for, these two charts over here. This is about 800,000 years of temperatures. And we can tell that from ice cores, we can tell that from tree rings, we can tell that from a lot of different sources that are out there. Notice the temperature goes up and down. We've had ice ages, we've had warming spells. Notice over here, the carbon dioxide goes up and down and up and down. And when the carbon dioxide is up, our heat is up. When our carbon dioxide is down, our temperature is down. They tend to go in lockstep. I'm not saying one causes the other, because it's, as you've seen, too complex, but notice we're going way up. We're higher than almost ever in the last million years in terms of our carbon. But notice this over here. Notice what was happening on the temperature gauge. Our temperature had spiked up and seemed to be coming down. We're actually in an ice age kind of environment along the way. So the planet Earth might have just saved our bacon to a certain extent, because we were already cooling as our industrial complex was putting things into the atmosphere to make us warmer. So that's where the real debate is. And this is the real scientific debate. I invite you, as you're thinking about this in the future, to pay attention more to people who are looking at the science and not looking at the politics. Because when I talk about this kind of stuff, I'm not going to mention Al Gore at all. I'm not going to mention any particular people who are doing anything political about it. And I know Al Gore initially was doing it mostly in science, but he was a politician, and thus he has that political veneer to him along the way. We do have a carbon issue. We need to figure out how to address it. We can look way back in history and see from craters, we can see from tree rings and ice cores and other ancient things like the stromatolites and coral reefs, what's happened in the past. And we can see that in different ways around our planet. And as we look around our planet, we see that we've been impacted from things outside. The Tunguska explosion, this is over in Siberia and Russia. If you've ever played the game of Risk and tried to hold on to the province of Kamchatka, that's where this is along the way. We had a big impact here. but it wasn't large enough to make a global change. Here's another impact that we had about 50,000 years ago. This is the visitor center over here, by the way. So this would be about the size of maybe Ellettsville, maybe even Bedford along the way. This was from something that was only 40 meters across, so not even half a football field large. But it was big and it was iron and it was chunky. The reason why this is still here is in Arizona, they don't have a lot of rain. They don't have anything to melt this away. Lots of craters like this become lakes and we don't notice them so much. Also, some craters like this are caused by volcanoes, but this one, we can tell from the debris that's in the middle there, was caused by an impact along the way. But we've had major, major impacts, and you may have seen Jurassic Park before, that came from the dinosaurs' extinction came from a huge impact in a place called Chicxulub, and that was off of the Mexican coast, right on the Mexican coast, in fact, about 65 million years ago. And it really changed our climate altogether. So we will talk more about some of the atmospheric and geological things as we look at cratered worlds and other terrestrial worlds, Venus and Mars. And we'll look more about atmospheres when we look at Jupiter and Saturn and the ice giants out beyond there. But I thank you for being part of this. And again, thank you for letting me stumble through our attempt with Zoom.